Hi, I'm Susanna Palitz. I'm an associate professor at the College of Information Studies, and I'm the director of the Organizational Teams and Technology Research Center, Research Society, and that's OTTRS. And can everyone hear me? Anyway, I am going to introduce, I'm really pleased to have, sorry, somebody texted me asking if there was a way to enable chat for the participants. But in the meantime, I'm going to I'm so happy to introduce Dr. Jessica Marquez, who actually was a former coworker of mine at NASA, and she's continued to do amazing, amazing things. Chat is enabled now. So since 2007, Dr. Marquez has been working at NASA Ames Research Center in the Human Systems Integration Division. As part of the Human-Computer Interaction Group, she's supported the development and deployment of planning and scheduling software for various space missions, including the International Space Station program. She leads a team that's developing Playbook, which is the name of a web-based planning, scheduling, and execution software tool. Her work has led to supporting different NASA analog missions, which she'll explain, that simulate planetary missions and spacewalks. Dr. Marquez is also a subject matter expert for space human factors engineering, specifically in human automation robotic integration. She lends her expertise across different NASA research programs like the Space Technology Research Institutes and the Human Research Program. She's currently the PI for a research project, Crew Autonomy through Self-Scheduling, Guidelines for Crew Scheduling Performance Envelope and Mitigation Strategies. Dr. Marquez has a PhD in Human Systems Engineering and an SM in Aeronautics Astronautics from the Massachusetts Institute of Technology and a BSc in Mechanical Engineering from Princeton University. And I'm going to mute myself, and please take it away.
Thank you, Suzanne. Thank you for having me and for taking the time to hear my pitch about promoting astronaut autonomy in human spaceflight. So I assume that not everybody knows what NASA is up to. So let's start with a little bit of inspiration. So where are we headed? So right now, the program that NASA is focused on, aside from our ISS program, is the Artemis program. And it's our program to return back to the moon. So hopefully this video will play and give you a nice summary.
We're going to the moon to explore, and we're going to the moon for scientific discovery. Our destiny is always to go and see what's further and what's next.
The moon is a stepping stone, and the moon is a place we need to learn how to live so that we can continue to go beyond.
We are focused. We are focused on all that lies before us. Only together will we bring to life this global ambition of returning to the moon. And while our work is far from finished, we've never been closer to seeing a new generation step beyond our home planet. We are building on the achievements of those who came before. The giants who conquered gravity and raised a banner in the heavens, they beckon us to go farther, to the moon and on to Mars, to seek a deeper understanding of our universe and bring all that we learn home. 2020 was a year of unpredictable hardships, and yet, step by step, we resolve to press forward toward this grand vision. The daily efforts of thousands of suppliers from all across this country and around the world fed into stunning milestones and laid the groundwork for history.
Launch team, go.
Artemis has been woven into our culture. It has fostered collaboration across the aisles and across the ponds. It has grown beyond plans and preparations to include hardware and software. And now it has a heartbeat. You can feel the momentum. It is undeniable. We are going. And together, we will see Artemis light the way.
Our mission to the moon is no longer some far-fetched dream. This is reality. We are going.
This is the next step in evolution.
They're not just PowerPoint slides. They're actually metals being bent, shaped, formed to build the things that we're going to use. This is real. This is going to happen. We're going.
We are going to the moon to learn how to live on other planets for the benefit of all.
Let's go.
So I hope
We're going.
you sort of got goosebumps with this video. I picked it. It's a little outdated, but I picked it because I think it articulates so nicely some of the themes that have been resonating with me over the last several years. And in particular, the phrase that resonates with me is how we're going to the moon to learn to live on other planets. And really, what does that mean exactly? What does it mean to live on another planet? And for me, it means not just staying alive, though it is an essential component. It is also being able to work and explore in space. And so these are sort of the drivers for why we want to do human spaceflight. So for human spaceflight, we need astronauts. We need astronauts, a variety of spacecraft that keep our astronauts alive, that gives them a place to live, allows them to explore. Even the tiniest spacecraft is our space suit that allows us to do spacewalks or extravehicular activities. And all of this is also interrelated with our Earthbound team, our flight controllers. Our flight controllers, our doctors, our scientists, our engineers, they're all providing support for the astronaut and the spacecraft, making sure that we are both supporting and caring for the astronauts and helping them and managing the spacecraft. So this is a very large team effort where we have people displaced back on Earth, back in space. And while this might be a little oversimplification of what it is to do human spaceflight operations, it is these three essential pillars of human spaceflight that need to work together in order to operate successfully and safely in space. So we need all three to live, work, and explore. So what happens when we look at this concept of operations and place it in the context of Mars? So there is one dramatic change when we look at missions that are going beyond low Earth orbit, beyond the moon, on our way to Mars. And that is that our way of communicating is going to dramatically change. This is going to be a disruption in our concept of operations. There's going to be several aspects of change. So one of them is just the physical distance between Earth and Mars will result in transmission delays. We can't cheat physics yet. And so there's going to be a long delay in the order of minutes between Earth and Mars, and even on the way. There's going to be limited bandwidth. We don't have nearly as many resources between these two planets to enable high bandwidth communication. So anything that has a video, for instance, or large data. And finally, there are also going to be periods of no communication when the sun is between Earth and Mars. It's really hard to send communication and data across the planets. So these changes in communication require NASA to really look and assess its concepts of operations and how we do mission ops for this context. So before I talk to you about what needs to change and how it relates to astronaut autonomy, which is the whole point of my talk, I first need to tell you a little bit about current operations. So this is our beautiful space station. In case you didn't know, it is about 150 miles right above us. It orbits Earth every 90 minutes. It is roughly 8 school bus rides or 1 football field if sports is your thing. It's been in existence for over 20 years. We've had continuous operation, but more like continuous people living there for 20 plus years. It's a national lab built in space by our astronauts, and it's a beautiful beacon of international collaboration. Many countries have contributed both people and resources to make this amazing vehicle that orbits our Earth. Now, as I said, there are people that are living there all the time. At any single point in time, there's either 3 to 7 people living on ISS 24/7. Their stay there is roughly in the order of 6 months, though some stay for much shorter periods of time, but roughly that amount of time. They do all sorts of things. This is a great snapshot of all the different variety of work that happens in space. They do regular things like sleep, eat, exercise, and most of their life is dictated by assigned tasks. So assigned tasks or activities, I might slip into that word. These assigned tasks are done in conjunction with mission control. So what's mission control? Mission control is a very, very large set of team members on the ground that are, again, helping manage the spacecraft and helping the astronauts all the time. So for ISS, or for the International Space Station, this is its main control center. This control center, this picture, this large picture, is at NASA Johnson Space Center in Houston. And each person here represents a different subsystem that is being monitored by a person on the ground. On top of that, each one of these persons has a back room, and the back room has another set of team of people that are providing them more detailed information in case anything comes up. There is a myriad of people because we want to make sure that there is the expertise available at the tips of their fingers at any one point. There is one role I did want to highlight. So here on the far right, I have pictures of a couple people in the back rooms. And then I wanted to mention the Capcom. The Capcom is a particular position in mission control, which is a person that is continuously talking to the astronauts. So the astronauts can talk to anybody, but they funnel all their information through one person. So they're able to then disseminate information accordingly. So this large team of people are supporting the spacecraft, are supporting operations, are supporting the crew so that they can do all the different variety of tasks that they do in space. So they're collaborating, coordinating, and cooperating between astronauts and ground teams. So what does that look like exactly? We will look at some of the activities that happen in space. By far, the riskiest activity that happens in space right now is EVAs or spacewalks. EVA stands for extravehicular activities. Spacewalks are highly coordinated. They are practiced on the ground extensively. They have a very detailed set of procedures. The procedures is just a very step-by-step instruction of what things need to be done. Everything that happens during an EVA is monitored. Everything, all the telemetry from the spacesuit, what the vehicle is doing, there's open voice comm all the time. So we're hearing the astronauts all the time. We're also seeing what the astronauts are seeing aside from cameras that are outside. And this is because the astronauts need to follow a very specific set of procedures, but also if something doesn't go right, everybody knows what's happening and we can quickly resolve this, this hiccup or work around the particular problem because there is a very finite amount of consumables that can be used to complete an EVA. The second riskiest activity is probably using the large robotic arm that exists on the space station. So this arm is called the SSRMS, which stands for Space Station Robotic Manipulator System. It's used for a variety of complex tasks. So we have maintenance tasks that happen outside. We have berthing activities where you basically have a visiting vehicle come up and it grapples the visiting vehicle and it brings it up to the space station and docks it or berths it. We also have astronauts that will be on the end effector, so basically the very tip of the robotic arm, to place them during a spacewalk in a location that they might otherwise not be able to reach. And so it's a very critical piece of tool in operations, one of the most complex things. But one of the things that people don't quite realize is that this is a very highly coordinated activity. So here we have a picture of an astronaut in front of the robotic workstation, and they have multiple views and they're able to manipulate those things. And usually the astronaut will do the part of the task that only requires them to do, small is the wrong word, but sort of be able to do the tasks that require that closed loop between a person observing the task and the robotic manipulation. But there's a huge amount of time that the robotic arm is actually coordinated and manipulated by the people on the ground. And so for complex tasks like capturing a vehicle or moving an astronaut, that is all heavily coordinated between the ground and the astronaut. One of the joys about living in space is that you get to be also a handyman on space. Like any place that you might have lived, your car, your house, when you have something that has existed for 20 years, 20 plus years, it needs maintenance. Astronauts spend a lot of their time doing maintenance work. And as you can see, these systems are complex, they're unique. And you know, not everybody, the astronauts get trained, but they're not necessarily expert mechanics on this particular system. So often they have very complex set of rules or procedures that they need to follow. And the ground is there to make sure, and they're verifying that things are working properly, that the steps are being done correctly, and to answer any question that might come about. Often these procedures are written in the context of Earth. And then when you get into space, you're trying to figure out, why did this is not quite working as it was explained in the procedure. Like, is there a workaround? Am I doing this incorrectly? And all these kind of questions, the ground comes in the loop to make sure that they are able to address any sort of question that might come about because of completing the task. And finally, astronauts do tons of science on space station. I particularly picked some of these pictures because they are of relevance to NASA Ames, which is where I'm from. So here we have an astronaut in with the Astronaut robot, which is a new robotic agent that we have sent up to space station. We have astronauts doing work in the rodent station, and then we also have a glove box here. And this is just to illustrate sort of the different variety of science tasks that they do. I particularly wanted to highlight this picture on the bottom right, because you can see the astronaut working in the glove box, holding this blue box, basically this blue, and it's their communicator. This is the way they actually call down to Earth. This is like their microphone to call down. But I want you to notice that she is doing a task in the glove box, holding the communicator, so clearly is communicating something to the ground about the task. And on top of that, if you look in the foreground, there is a picture of a video camera directly pointing at the glove box. So in any sort of science task, if there are questions, they're usually looping in the scientist, or they're looping in the payload specialist for the science task that they're doing. So they get feedback and they are allowed to ask questions in order to make sure that the science gets done right. So hopefully I've given you an overall picture of how essential communication, collaboration, and coordination is in spaceflight, in human spaceflight. But I think the biggest takeaway that I'd like to make sure you got from that is that in order for us, our current concept of it, in order for us to work safely for our vehicles and our crew members, we have a concept of operations that is highly dependent on our communication infrastructure, which is one that is frequent, constant, high bandwidth. And so when we look at that and say, okay, what if we're disrupting this fundamental component of collaboration, how does that change? So we need to move from becoming Earth reliant and Earth independent. And that requires us to develop new technologies and new concepts of operation. When we talk about that in the context of spacecraft, we're talking about new, different and diverse spaceships, landers, rovers, robotics, spacesuits. But we're also talking about making them more capable. So having an increased use of automated and autonomous systems. When we talk about it in the context of astronauts and spacecrafts, we talk about better human systems integration. New systems that will help the astronauts manage the vehicle. So right now, the flight controllers are managing a huge amount of the spacecraft. We need systems to facilitate this management of the spacecraft to the astronauts, particularly to to help them identify fault detection, isolation, and resolution of anomalies. When we look at this from the context of the astronauts and their ground team, we start talking about things like communicating, developing tools to better communicate, coordinate, and collaborate across a diverse set of tasks. And overall, what this means is that there needs to be astronaut autonomy integrated into our concept of operations. Astronaut autonomy, for me, is specifically the ability to work more independently from mission control. And there are new technologies that have to be applied in all of these different areas. Now, I don't claim to contribute to all of those areas, but I wanted to highlight for the rest of the presentation some of the work that my team and myself have done in order to promote astronaut autonomy and trying to tackle different aspects of this work. I also wanted to make sure that I told you about the fact that I come from a human-centered design process. I'm in the part of the HCI team, the Human-Computer Interaction team, and we follow HCI principles. And so so that means that I and my team and my group depend on research, design, development, user testing and deploying, and doing an iterative deployment software process in order to make sure that our tools work for astronauts and flight controllers. So our emphasis is doing observations of working operations and doing a lot of usability testing as well. Now, I know I'm talking really fast, but now, why, Jessica, how can you do observations of work for things that never happened? Like, we haven't gone to Mars, we haven't returned to the moon yet. How can you do observations of work? So we can do some observations, and a lot of our work has depended on doing observations in Earth analog environments. So what's an Earth analog environment? An Earth analog environment is a particular analog that simulates one or more specific aspects of space flight. So it might be things like a remote extreme environment. It might be isolation. It might be a place where it's really dangerous. So taking some element of spaceflight and in making it an analog is what I refer to as an Earth analog environment. And NASA does many of these in different places and does simulate different aspects of human spaceflight. Okay, so the first project I'd like to briefly tell you about is improving procedure execution tools. So as I said, a procedure is a very long, complicated list of step-by-step instructions for an astronaut to do. So in our work, we're looking beyond just like, can we make these steps easier to understand? That's of course, like linguistically, something that could be done. But what we are looking at from the HCI perspective is how we can leverage new technologies to provide information about procedure, step, execution, and correctness. So sort of the side of like adding support for execution itself. So the picture here shows an astronaut actually reading through a procedure on their tablet. So the kind of technologies that we've been looking at have been the Internet of Things, so an integrated suite of sensors using augmented reality displays and haptic and oral feedback. Our work has centered around 4 research projects that are anywhere from low to medium fidelity, usability studies on prototypes. And so what I wanted to make sure I pointed out is like we have a few publications if you'd like to read a little bit more about this. But I also like highlighting this work because it actually is, a lot of it has been done by high school undergraduates and graduate students in order to do these demos. So the first one I'd like, this is one of the very first projects our team did, which is integrating IoT technology. So one of the things that we wanted to demonstrate is the fact that we could instrument tools and we can instrument people and give them quick feedback about both the correct selection of the tools. So if the person selected the right tool, then they would get an actual haptic feedback, a buzz on their arm saying, yep, that's the right tool. And then also like making sure that they did the procedure in the right order. And so they would get feedback about it being right or wrong. And that was just really a demonstration that that was feasible to do. And then in the next one, we looked at using AR or augmented reality to help explain visually complex procedural steps. So imagine having to write that explanation or even just look at how the orientation of that piece is, which is actually based on a real ISS procedure. You can instantly really recognize that work, what you need to do using AR, as opposed to trying to explain that in words or even pictures. We're currently having an experiment in one of the analogs called HERA. I'll talk a little bit about HERA a little later, but we have a research experiment in HERA, which is looking at integrating complex procedural tasks and embedded sensors. So we're really putting all of these demonstrations together into an actual procedure that is a complex procedure. So we're looking at a mechanical repair task of a generator and showing how all of these systems can work together in order to assess and improve performance of an astronaut doing a complex task. And so we're right now evaluating that in HERA, and so we're still collecting data on the results of that. The second project I'd like to talk to you about a little bit about is improving communication tools. So as I mentioned before, that little blue box is the communicator. Most of the communication that happens between ISS and the ground is voice and video. Voice allows the astronauts to communicate with the Capcom. And really, space-to-ground texting is relatively uncommon in spaceflight. One of the things that we have learned from participating in all of these different types of analogs that simulate communication transmission delays is that text is easier to manage than voice communications. And a lot of you probably can resonate to that as you text people and people get back to you later. There is just a way of having a record that you can then respond to later. However, we hold that ordinary chat interfaces need to have enhancements to better support transmission delays because it's not actually sufficient to use what I call ordinary chats. So our team has built a communication tool called the mission log. This emerged from our work in analog, and it has some elements that are common to chat interfaces. It has multimedia, so you can send pictures and text. You have the standard timestamps, and you can do searches. But it also has some unique features that are supporting transmission delays. So we have things like counters for received and earliest, user-driven acknowledgements, and prioritization of messages. So imagine if you send a message and it's urgent for someone to respond back, and you're delayed 4 minutes. Trying to figure out trying to do all that time math to understand when is the earliest time someone can respond to you when you're in an environment like an analog is not easy. And keeping those numbers in your head is not something you want to spend your brain power on. And so our tool makes it easier to say, has the message been sent? When do they expect it to arrive? And when is the earliest that you can expect a response? And so we have all that embedded in the communication. We've actually deployed this tool in a variety of analogs. We've done it in NEMO, which is an underwater analog, and we've also done it in an analog called Basalt to support planetary EVA and science support. I'm going to highlight Basalt here right now. Basalt acronym is Biologic Analog Science Association with Lava Terrains Research. And this program focuses on how we support and enable scientific exploration during Mars missions. I highly encourage you, if you're interested in Basalt, I highly encourage you to look at our publications. There are many of them. It's a fascinating analog that was done 3 times a few years ago. And so basically what we're doing is we're simulating people being on Mars, and we have like astronauts that are exploring a remote terrain. And then we have our astronauts that are in like the habitat, in the Mars habitat. And then we simulate delaying the information that's coming from the Mars side, everything from pictures, video, voice, text, all of that gets delayed and sent back to a team that is on the Earth side. And they're helping the astronauts make good science choices on exploration. All our scientists might not, all our astronauts on Mars might not be expert geologists, might not be expert biochemists. And all of that expertise that resides on Earth needs to communicate. They need to see what they're doing and needs to communicate back to the astronauts so that they can make the best out of their mission. So in this analog, the particular aspect that we simulated was the delay between Earth and the quote unquote Mars side. We did 2 types of latencies, 5 minutes and 15 minutes, and mission log was using all 3 deployments. So some of the things that we learned, again, I'll point to you in my publications if you're more interested. What we learned is that, texting and mission log enabled communication across this mission delays. You can read and respond more readily. You can have traceability for recommendations, which was really important. It provides you insight as to when messages could have an impact on future tasks. That was also very tricky to do. Again, a lot of math, time math that you need to try to figure out. And another one that I like to highlight is the fact that sometimes pictures are worth 1,000 words. Being able to communicate using multimedia was valuable. Okay. So I wanted to quickly go through my last project because I want to make sure that I give time for questions. But I could talk about enabling self-scheduling for a long time because it's the big project that we work on right now. So let's see. First, let's start with this video.
Summary, and next, I look at our schedule. Here it is, the bars. Oh, the bars. These bars run my life. They control everything right here. This is what controls everything. The red line in the center, I don't know if you can see that. Yeah, you probably can. The red line in the center is the current time. So it's 5 minutes after 7 a.m. It tells me if it's day or night. It tells me what I'm supposed to be doing. It tells me if I'm late, if I'm early, which rarely ever happens. It tells me if I have communication coverage. It just tells everything I need to know, and I can look at my whole day by just scrolling ahead. It tells me when I'm going to be getting email. It tells me everything. I mean, the bars, they just run your life, and they go by so fast, you can't stop them. And the red line, no matter what I do, it just keeps moving and moving to the right. I can't stop it. I just can't. Oh, get a grip, Reachman. Oh, for crying out loud. The space dimension's got a hold of you. Oh, it's only another month. You can do it. Get a grip. Sorry about that. I'm okay now. I'm fine. So anyway, these bars tell you, what's going on next. So I got some morning prep work, and we have a daily planning conference. So in between, hope to squeeze in some breakfast. I don't know about you, but I really could use some coffee to wake up this morning. So what do you say we head over to the Russian segment and get some breakfast?
So I hope you were all amused at this video as much as I do, but it's such an excellent motivator for the work that we do. So what astronaut Garrett Reisman was saying was the bars. The bars are actually activities. They're assigned activities that the astronaut has to do. And it does dictate their life because they are dozens and dozens of people on the ground that have carefully crafted a set of activities for astronauts to do in space station to make sure that there are enough resources and all the constraints are met in this timeline, basically creating a schedule that is actually doable. Space station is a very complicated place, but it still has many constraints and there's limited resources. There aren't an infinite amount of computers. There aren't an infinite number of video channels to communicate back and forth from space station to ground. And so these schedules are basically the rules and activities that the astronauts have to follow. So the concept of self-scheduling, which is a concept that we sort of coined, is really to try to shift some of this ownership of the schedule to the astronaut. So move that ownership in a way that they can manage their own schedule. So imagine you have a calendar and someone else dictates your whole entire calendar. This is basically starting to open the door to allow astronauts to provide their input into their schedule. And why is this valuable? This is valuable because we think it can mitigate some of the effects of communication and allows the astronaut to contribute insight as to how best to manage their schedule. So imagine if you're doing an activity, but you're running late or you finish something early. Do you want to spend idle time, waiting for mission control to respond as to what to do next? Or can you figure out how to best make the most out of your time? So this is why we think it's a benefit. But then there's also all sorts of challenges associated with this. It's a very different concept of operation. We don't really allow astronauts to manage their own schedule in that way. So it requires new protocols. We also don't want to overwhelm the astronauts because they're not expert mission planners. We've had weeks and weeks and dozens people to create this timeline. We don't want to overwhelm the astronaut. And then finally, if an astronaut does choose to reschedule something, we want to make sure that we retain the constraints. We want to have a plan that abides to the constraints. So in the area of self-scheduling, we've looked at sort of a progressive set of evolution. We've developed the tools, we've done feasibility assessments, we've done performance measures and controlled experiments, and now we're looking at the mission level impact assessments. So this is Playbook, this is our tool. We've been working on this for about 10 years. And it really, we've been field testing this across multiple analogs, resulting in an easy to use next generation scheduling and timeline tool. I'm gonna skip the video, which is just showing you how we use Playbook, just so that I make sure we have time for some questions. So one of the big places that we used Playbook to demonstrate self-scheduling is in an analog called NEMO. They're doing a variety of science tasks. And over the course of several NEMOs, we've asked astronauts to manage their own schedule, be it science, be it their dives. It's the tool that is used for the whole entire operation. And this, over the course of many years, allowed us to mature our product in such a way where we then were able to use and do self-scheduling in space with an actual astronaut in space station with an actual timeline for ISS. That's really big for us because we are being able to demonstrate that in a realistic environment, we can actually do this type of work. And so we did this back in 2016. And we deployed Playbook. They did 5 incrementally difficult self-scheduling exercises in order to assess the effect of the concept of operation, really. This is what Playbook looks like with an ISS schedule. It is massive. And then the astronauts were asked to move their activities that were prioritized into their schedule, and the activities were prioritized. So we successfully did this. And what we found is that Playbook provided a low entry barrier for self-scheduling for an ISS timeline. This is the first time an astronaut has self-scheduled in space. I included a picture of myself here because this is one of my career highlights, really. To have a little piece of my work be in space is really, really cool. We also identified that we need new visualizations to support some of these complex constraints in operations, in spaceflight operations that we don't see in analogs. And sort of one of the things, because we collaborated in this project with Mission Flight Operations Directorate at NASA Johnson Space Center, that actually providing flexibility resulted in a lot of overhead on the ground support team. We have a couple publications, one specifically detailing all the lessons learned. So please, again, feel free to look at those if you want more information. We have also managed to have a controlled experiment to look at the effects of individual complexities related to constraints. We have data on that, and we've published those too as well. The big takeaways from our research is that the more constraints we have, the higher the workload, lower efficiency and lower effectiveness. And one of the things that we also are still trying to figure out is how we capture and differentiate all the different effects based on the different types of constraints. So the type of constraints they have to solve against actually had different various effects across the different schedules. So that's just one aspect of our work. We're also have developed different visualizations based on that controlled experiment. There's the no-go zones, there's suggested fixes, and network move. A lot of them are mixed initiative scheduling. I'm sorry, I'm moving really quickly through these, mostly because I just want to make sure I answer your questions. And finally, there is currently we're doing another research in HERA. HERA is called the Human Exploration Research Analog. You can see the picture of the building there. There are four crew members that live in this habitat for 45 days. They have multiple missions, and Playbook is being used operationally. And we are also have the opportunity to ask the crew members to do specific self-scheduling, but then we also allow them to do self-scheduling for most of the mission. So this is the first time we're able to see how self-scheduling will impact the whole entire mission operations, which is something that we couldn't really do in service in space station. But this allows us to open the door and understand some of the challenges that come about when we change the concept of operations at a mission level. Okay, so I hope that that from this talk you get this big takeaway that astronaut autonomy is a key component to moving from Earth reliant to Earth independent missions. And if we're really truly going to the moon to live on other planets, we need to start enabling astronaut autonomy from all the way from the moon to take us all the way to Mars. I know I threw out a lot of citations, a lot of information, but if you have any questions, I'm happy to answer them right now. Everything in this slide deck comes from either NASA or one or more of my publications. So I'm happy to also share those with you. And with that, I'm going to end sharing so I can answer questions.
Thank you, Jessica. or Dr. Marquez, I will go ahead and moderate. There's only one question in the QA yet, though there were a couple comments in the chat. People are really impressed with the user video. An anonymous attendee asks, are any of these scheduler tools available outside of NASA? I see utility for large enterprise software development programs where you have restrictions on downtime and so on.
So most of the work that NASA does is available There are a lot of different sort of set of rules, but there is a website, and I can't remember the website right now, where you can look at what are all the software tools that are available from NASA. Sorry, I don't have that at the tip of my fingers, but there are ways to try to assess and whether they're allowed to be shared out.
Cool. Do other people have questions? Another anonymous attendee asks, how is NASA leveraging the tech industry to improve some of these tools and future tools, potentially?
Yeah, so it's interesting because often NASA reacts to the technology that is emerging. So for instance, one of the great stories was when tablets started emerging, right? Like that happened, I think probably under 10 years ago. And the iPad is, started emerging. And then all of a sudden, the astronauts were like, we need iPads. These are the perfect hardware for spaceflight because they're not tied to a location. When you have a laptop, you have to physically tie it down in the space station. You can't move it and take it around. You're floating in space in multiple orientations. An iPad is the perfect hardware for them because they can easily carry it. They can easily attach it and Velcro it to different orientations. They could put it on their legs. They took it from their legs and then they can put it up on different payload racks. So often what happens is as the technology matures out in industry, NASA then says, hey, can we use that? And then there's a sort of a ramp up because not everything can be used in space. But iPads happen to be very work fine in space. So they were able to send them, and now everybody had to play catch up. They're like, okay, what software tools can we use on these devices? And so basically then NASA had to go back and fix their software to make sure that they're able to work on those platforms. And I see sort of a similar pattern coming about in some of these other new technologies that are emerging, which is why we wanted to explore that in execution tools, for instance. We see a similar thing about AR and VR. It's like, oh, the technology is suddenly very reachable and usable, and then like, great, let's try it out. And then as soon as you send it to space, you realize, oh wait, we still have a few things that we still need to figure out. This is not quite as robust as we thought it was. And then we get all the same effects that we get here on the ground. People get motion sick or have hard time doing the co-reference that you need to do in order to have things align itself. And so there's a variety of things like that where a lot of times it's NASA needs to go out and search these technologies and assess them before they're integrated into operations.
I
hope that answered the question.
I hope so. I have a question, and then we'll get to Joelle's question. It's clear that there's a lot of domain knowledge necessary in trying to make tools for this group of people. And how do y'all, as HCI folks, gain all that domain knowledge?
So it's just, so our team has done it particularly by being involved in the analogs. I think the other advantage was that we also worked on actual space flight tools. And so I think the combination of those things has allowed us to do sort of the spectrum of work, which is we do basic research. So we might do things that are like, okay, I have a timeline with these constraints. I could do the very basic research to understand the performance. How does then that apply to something that's applied? Okay, and then here we can use the analog environments, and we have all that experience there. And then we have our experience with actual operations and seeing the actual way that people do work and trying to understand and extrapolate how those then would be for a future mission. And so I think we've been lucky to be able to sort of look at all those different phases of development in order to both provide our insight for future, and as well as making sure that we still stay in line with current operations.
Very cool.
Also, we also work with an HCI program, and we do also encourage them to, for instance, find analogous domains so that they can, so again, try to find the particular aspect that you're interested in, like the particular challenge that you're wanting to explore. And it's pretty sure, almost always, that particular aspect of work can be found in other analogous domains. Working under pressure. Right now, one of the things that I'm interested in is sort of like, how do we better support doing exploration, both like doing spacewalks that actually have a changing dynamic environment. An analogous domain could very much be wildfire management, right? Like where the situation is changing pretty frequently. How is all that information getting fed back into your displays, into your information infrastructure? How do you best display that information as it changes over time?
Yeah, that's very cool. I know that we probably have some graduate students and undergrads here, which is why I was sort of trying to, how can people kind of learn these things? Joel Chan asks, curious about the tension between the inherent uncertainty and open-endedness of ill-defined exploratory research versus the strategy of reducing coupling, my translation, promoting astronaut autonomy. Are highly independent autonomous missions possible only for a limited range of open-ended missions? And then he mentions inspiration is there's a speed limit for human computational approaches and crowdsourcing for well-defined versus ill-defined structured work. And he has a link to that article. I think you can see it. Great.
Yeah. Oh, I haven't looked at it.
That's okay.
I think there is a natural tension, right? Because one of the things that I probably did not highlight enough is that NASA is very risk adverse. Safety is always a big driver, right? We don't want there to be a next accident. We want to make sure that we're protecting our astronauts and our vehicles, which are, again, keeping our astronauts alive as much as possible. And so there's always a tension between safety and exploration and autonomy. And so I think overall, there is going to be a natural tension always among these components. I remember I have similar conversations where people say, hey, the most important thing is to keep the astronaut alive, because if I can't keep them alive, they're not ever going to do any work. And I'm like, yes, that is true. However, the safest thing to do is to not launch them, right? So we have to take certain amount of risk to be able to not just be alive, but to also work, because that's the whole point of going, to actually work and explore. I'm not quite sure I answered their question, but I think the short answer is yes, there is tension, and I'm not sure I touched on the particular aspects of autonomy that they were interested in.
Joel says in the chat, super helpful to understand the context. Thanks, a smiley face.
Good.
James Grand has a question, which is, I understand there's often interdependencies among astronauts' tasks, i.e. tasks that involve more than one astronaut to participate at the same time. A particular task needs to be accomplished by a particular person before some other task, or a person participates, but not sure. If so, what are the challenges, considerations for self-scheduling these more interdependent tasks?
Yeah, so that's actually really interesting, because we've been doing our research about like how we perform to do self-scheduling and enabling it. And then we have recently a lot more research that comes in the area of team dynamics, and they're looking at like how coordinating activities with two people, or the order of tasks that might affect team performance. And all of these things are interrelated. And I'm literally just learning about some of these interrelationships, and they're really fascinating. A lot of people are like, oh, they're proposing countermeasures that are about scheduling. And sometimes it's like, oh, but these schedules are so driven by operational needs. And so it's actually super fascinating to me. Of course, when you have, if you think of people as resources, like the more resources you use, the more constrained a particular activity is, the harder it is to schedule. So basically the most constrained activities are the hardest to schedule. So resources can be people, they could be time, they could be physical resources like communications, recently I was just looking at a current schedule for the space station, and every astronaut has to do like 2-ish hours of exercise, and there's 7 people on space station. How do you find 14 hours where that treadmill is available, where that weight system is available? So yeah, resources makes it more challenging. But I think also the whole aspect of like, how do we allow scheduling to enable teamwork and better work performance is a whole new area for me, and I think it's really interesting.
I seem to remember when y'all created the playbook for the Mars exploration rover missions, which had to do with rover tasks, you put in the dependencies into the software, right? Yeah.
So one thing that I didn't mention, I didn't mention it actually, is that we do constraint checking. So if an astronaut moves an activity and puts it in the wrong place, they do get a violation marker. They do say, hey, this isn't going to work. You need to move this activity, and the visualizations that we're developing will help them facilitate where to schedule that. Sorry, yes, that's very true. We do model constraints in our system.
I'm like, I know you've done this for decades now. Yeah, so that's really cool. There's one more question on the chat, and we'll do that, and then we'll say thank you because it's 1 o'clock. What are some opportunities in this space? And then paired with that is what kinds of HCI techniques do you think are good and difficult to apply in this problem space?
So really quick on the first one, NASA has started to do challenges. These NASA challenges are actually open to the public. So if you Google NASA challenges, these will be opportunities that perhaps students might want to jump into or explore. But to me, one of the hardest things for HCI as an HCI practitioner is, again, like Susanna hinted, is getting that exposure to real work. Being able to observe ISS operations in real time is really challenging. It's very time limited. We also don't want to disturb people doing very critical work. And so I think that's one of the aspects that's the hardest. And then sort of abutted to that is the fact that often our designs and ideas hit a roadblock with regards to software. A lot of the software that are being used are legacy software. So you might have an idea to be like, oh, I could make this particular UI, but the infrastructure isn't there to enable that development. So a lot of times we have to work with the legacy system so that we can move them into sort of like the next generation of software. And so I think those are 2 things that I find the hardest as an HCI practitioner. But thank you so much for having me. I'm so glad I was able to talk to y'all.
Thank you for coming. And if any of you have opportunities for students or graduate students, you know where to find us. But thank you so much for coming and talking and sharing this really cool work that y'all do. And yeah.
And feel free to send me an email if you want the citations more specifically. I try to respond to all the emails. So if I get to you late, it's because there's just a lot, get a lot of emails, but I will try my very best to reply to most people.
Do you have a website with like links to some of your publications? And then people don't have to bug you. No,
I'm not quite that savvy academically.
That's cool.
But
yeah,
a lot of about 90% of my work is on the NTRS, which is the NASA Technical Server Repository. It's where all our NASA funded work gets available. So if you search there under my full name, you'll get a hit for all my publications.
I just put that in the chat. Just found it, folks.
Yes.
Okay, well, thank you everyone for coming and participating, and thank you so much for coming and speaking to our group and everyone.